Hey, Vsauce! Michael here. Oh, don't mind me, I'm just practicing my social distancing. You know, all the free time that I have now, to be honest, I've been getting a lot more sleep.
Or, I've been reading a good book. Shelf. What is a shelf? And what makes a shelf? Shelf. To understand what makes a shelf, we need to first look into what physically makes up a shelf. Well, anything really. It can be made of wood, plastic, metal, whatever. The whole point is to choose the right material for the right application. For example, let's take this wall-mounted shelf. It is located in building E2 of the University of Waterloo campus. It spans about 3.15 meters and is of a simple yet interesting design. The top surface is made from 6 long metal rods which lay on 5 evenly spaced truss structures. Each truss is made of a single bent piece of sheet metal and as well as a second vertical piece of sheet metal as shown here. Each truss is secured to the wall by fasteners. The shelf is specifically located in the hallways of E2, an environment which is generally dry and sometimes a bit musty, so the corrosion due to moisture won't be very extreme. The extent of any possible corrosion will be limited to daily exposure to cleaning fluids from the janitorial staff, or the occasional sprinkler water from potential fire alarms during the building's lifetime. E2 has quite a few labs, so the contents being placed on the shelves might be heavier than normal. The fact that the shelves are fully metal could possibly mean that they were designed to support heavier loads than usual. Now, what does this have to do with identifying the material? Well, since we can't look up what the specific shelf is made out of, we need to make an educated guess. Knowing how this shelf is used helps us identify what possible material it can be made from. Based on its location, the shelf isn't undergoing any insane loading conditions, and they would want to avoid replacing it due to any possible corrosion. Therefore, it would be most likely made from a stainless steel or an aluminum alloy. However, based on the fact that it noticeably deflected upon sitting upon, it is suspected to be made from aluminum. To support, aluminum was rising in popularity for all sorts of applications, including construction, during the late 1950s to the 1970s, and E2 was built during the 1960s, so most likely it could be made of aluminum. Visibly, the shelf has also managed to successfully mitigate any corrosion, including corrosion from exposure to moisture, stress cells, and crevice corrosion near the bolted connections. By choosing the shelf to be made of aluminum, it can successfully protect itself from corrosion due to the thin aluminum oxide layer that forms once exposed to the atmosphere. It could be made of most aluminum alloys, like 5032 or 6061. However, we suspect it to be made of 3003 H14 aluminum, one of the most common 3000 series aluminum alloys. Its key difference from other alloys is its excellent formability while maintaining moderately high strength and being cheaper as a sheet metal. We can also analyze how this shelf was manufactured. The sheet metal was initially rolled from an ingot into a plate on what's known as a breakdown mill, and then further cold rolled until it reached its desired sheet thickness. 3000 series aluminum cannot be annealed, so it gains its hardness and strength from cold working only. Cold working increases the dislocation density and changes the grain geometry, which limits dislocation movement and thus deformation as well, thereby increasing heart strength and hardness. The H14 temper designates that it's been strain hardened without any subsequent processing to about 50% the level of a full hard temper. Once the sheet metal is ready, it is then cut into the desired rectangular strips, and one of them is bent into the desired truss shape. The truss is then welded together with the long aluminum rods on top. If there were any surface treatment process, it would occur now, as coated material cannot be welded. However, a coating is not needed as aluminum is naturally corrosion resistant. Well, since we know that the shelf is made out of 3003 series aluminum, then it must be the best possible material for the shelf. Or is it?
We can find the optimal material by undergoing a material selection process using CES EduPack software. This metal shelf is installed indoors where it can expect room temperature, little moisture, and no abnormal chemical exposure. Mechanically, it can expect moderate loads including equipment and full-grown adults, since it is low enough to sit on. No extreme loading is expected because of the lack of space on the shelf, and more importantly because of the danger it would expose to pedestrians. The following are the metal shelf's functional requirements. The shelf should sustain a load of 685 pounds, which is equivalent to 5 average adults sitting on it. The load sufficiently accounts for general equipment. For example, a small printer is 4.4 pounds. The shelf should not deflect more than 1 centimeter. The shelf should last the lifetime of the building, and the average lifespan of a concrete building is 50 years. The raw material cost should be less than $6, which is equivalent to a $60 metal shelf with 10% raw material cost. Lastly, the object is made from sheet metal that is assembled through bending and welding. This constrains the material to have a width of at least 2 centimeters and a height of 4 millimeters. Our main objective is to minimize cost, which allows large-scale manufacturing and low retail prices while maintaining profits. Our target audience would be large institutions who want a cost-efficient option for having shelves installed across their many buildings. The objective cost equation is as follows. Cost equals height times base times length times cost per volume. Our free variable is the cross-sectional area of the strut members. Since the height is restricted to 4 millimeters, the strut members that make up the shelf will vary only in the horizontal direction as shown in the picture. Here are the limits relating to the material family, processing properties, and thermal properties. The material must be metal for the following reasons. Metal is ductile, meaning it will show signs of deformation before failing, which allows users to repair or replace it before any accidents occur. Metals also generally have good strength and are long-lasting. As for processing properties, the material has to be excellent at cold and hot forming, since that is how sheet metal is commonly manufactured. The material should also have good or excellent weldability, since the metal shelf was assembled through bending and welding. Lastly, the material should have a melting point of over 600 degrees Celsius, which is the average temperature of a building fire. This greatly increases the chance of the shelf surviving the incident. Here, we have the functional requirements for buckling failure, yield strength failure, and beam deflection. The shelf has been simplified into a truss structure for force analysis. The total load of the metal shelf was 685 pounds, which means that each of the 5 trusses will receive a load of 137 pounds each. The loading scenario for both buckling and yield strength failure has a divided load of 68.5 pounds on joint C and joint A. From force analysis, the largest compressive force is on member DB, which will be used for buckling failure, and the largest tensile force is on member AC, which will be used for yield strength failure. For beam deflection, the 137-pound load is placed on joint C, where it will generate the maximum moment on the object. By looking at the loading scenarios, we can identify the corresponding formulas. From applying the limits and functional requirements, we can generate the material performance indices. Here is the MPI graph for beam deflection. It can be seen that there are only groups of steel and aluminum remaining. It is known that aluminum has a built-in quality of corrosion resistance, which means it does not have to undergo further processing procedures to gain those wanted corrosion-resistant properties, such as through coating. Through our research, it was found that the manufacturing of steel is still overall cheaper than aluminum, despite the fact that steel requires additional processes to gain corrosion-resistant properties. Therefore, this allows us to remove the groups of aluminum at the bottom. Looking at the graph, we can see that the groups of steel generally have the same Young's modulus, but are priced differently. By reading the x-axis, our ideal material is located near the top left of the graph. Since our main objective was to minimize costs, we can set a price limit of less than $10,000 Canadian dollars per meters cubed to narrow down our options. This leaves us with this group of steel at the top left to choose from. The remaining material generally have the same material properties and costs. Therefore, it can be said that any of these materials are suitable for our application. But since we can only choose one material, we will choose the one with the best overall material properties. By looking at the yield strength MPI, we can see that there's a wide spread in the material data. We can simply choose the material that stands out above the rest, which should be the topmost material on this graph. And so, the final material selected is low alloy steel that has been oil quenched and tempered at 205 degrees Celsius.
Before we discuss the final material, let's talk about some of the pros of 3003 aluminum
to see why it might have been chosen for the shelf. Firstly, it is light in comparison to the low alloy steel, which is about 4 times denser. It is also strong since it is used to make chassis and boat hulls. Its malleability allows it to be formed into intricate shapes, and the layer of aluminum oxide that forms provides natural corrosion resistance, which is a great plus for cost savings. For the low alloy steel, it was mentioned earlier that it is cheaper than aluminum. It also has high strength since it is used for more rigorous applications. As found before, the Young's modulus is higher than aluminum for the same price. And finally, high hardness helps resist scratching, which can lead to crevice corrosion. In our case, what we're trying to do is minimize cost, so the cheaper the better. The mass of the shelf is not constrained, therefore it can be ruled out as a factor. The shelf can be made out of a neutron star as long as it's inexpensive. Since the shelf has a simple design, the material only needs to be rolled into sheets, bent, and welded. As we've seen from the limits, both materials can be welded, cold and hot formed. Lastly, the dry and temperature regulated environment means that the material's corrosion resistance has less of an influence as well. Knowing all this, we can cross out the lightness, malleability, and corrosion resistance of aluminum as big factors in our decision. Overall, we have more advantages using low alloy steel. Therefore, we feel it is a more suitable material. For the heat treatment of our steel, it first undergoes tempering. The steel is heated and held at 205 degrees Celsius for a specific amount of time in order to decrease hardness or increase ductility resulting from prior processing. It also relieves the stress on welded and work-hardened components, which applies directly to the manufacturing of the shelf. Commonly, the steel is in its martensitic phase, a non-equilibrium state supersaturated with carbon. Tempering allows that carbon to disperse, decomposing the martensite into its equilibrium states. The process is then followed by rapid cooling to further control the properties. Quenching is the process of rapidly cooling a metal in some medium after it is heated in order to control which microstructures, and therefore properties, are present in the final state. Generally, quenching increases hardness since the surface is what cools first. The other final properties depend on the cooling rate, which differs by quenching medium. In this case, the low alloy steel is quenched in oil, which cools faster than air but slower than water. Oil is also a fire hazard, so caution must always be taken. As for surface finish, hot dip galvanizing and painting are two viable methods for corrosion protection. Although painting might seem like the cheaper option, maintenance costs over time are higher than galvanization. The overall cost of galvanization has gone down over the years, thanks to the low cost of zinc and improvements in the process. This means that you can have no maintenance costs for up to 70 years. Since the shelf is located in fairly corrosion-free environment, either option can be used.
So, where does this put us? Well, now that we know that the best possible material is ultimately decided by its application. Just like a shelf, we humans are also at our best when we apply ourselves in the right manner. So, for the next few weeks, stay inside, snuggle up under a nice warm blanket, and pick up a good book. Not only will you save others, but your shelf as well. And as always, thanks for watching.